and then access the data from programs that were preemptively copied into the DRAM in a few nanoseconds. For example, many video games have a loading time to start up the game itself, and then a separate loading time to load a save file. During the process of loading a save file, all the 3D models, textures, and the environment of your game state are moved from the SSD into DRAM, so any of it can be accessed in a few nanoseconds, which is why video games have DRAM capacity requirements. Just imagine, without DRAM, playing a game would be 3,000 times slower. We covered solid-state drives in other videos, so in this video we're going to take a deep dive into this 16 gigabyte stick of DRAM. First, we'll see exactly how the CPU communicates and moves data from an SSD to DRAM. Then we'll open up a DRAM microchip and see how billions of memory cells are organized into banks, and how data is written to and read from groups of memory cells. In the process, we'll dive into the nanoscopic structures inside individual memory cells and see how each capacitor physically stores one bit of data. Finally, we'll explore some breakthroughs and optimizations, such as the burst buffer and folded DRAM layouts, that enable DRAM to move data around at incredible speeds. A few quick notes. First, you can find similar DRAM chips inside GPUs, smartphones, and many other devices, but with different optimizations. As examples, GPU DRAM, or VRAM, located all around the GPU chip, has a larger bandwidth and can read and write simultaneously, but operates at a lower frequency. And DRAM in your smartphone is stacked on top of the CPU and is optimized for smaller packaging and lower power consumption. Second, this video is sponsored by Crucial. Although they gave me this stick of DRAM to model and use in the video, the content was independently researched and not influenced by them. Third, there are faster memory structures in your CPU called cache memory, and even faster registers. All these types of memory create a memory hierarchy, with the main trade-off being speed versus capacity, while keeping prices affordable to consumers and optimizing the size of each microchip for manufacturing.